Our next speaker is my colleague, Professor Kemshwar Pula. Professor Pula is a distinguished professor of mechanical engineering at UC Berkeley, and he will talk about sharing mobile electricity storage for grid services.
So first, I'd like to thank the DTI and C3 for supporting our research. This is a project with Utkarsha Agwan, who's sitting over there, Junji Quinn, who was my postdoc. He is now at Purdue, and myself. And these are just the people who are on the proposal, but we got a fair bit of help from people who were not on the proposal. Praveen Varaya, our fearless leader, and Kostas Panos, whose singular talent is to inject reality into every theoretical formulation. And or another way to put it is puncturing balloons. That's what he has a needle in his pocket. It's a very simple idea. Electricity storage is very expensive. So it's $130 per kilowatt hour. It makes up a huge portion of the cost of your Tesla or electric vehicle. Electricity storage is very expensive. So there are many use cases for electricity storage. For example, electric vehicles. But you know, how often do we drive our electric vehicle? 2 hours a day, okay? Utility scale batteries are used to deal with ramp up and ramp down capability, maybe twice a day. Price arbitrage, a couple of times a day. And of course, the price differences aren't great. The bottom line is you're not using batteries that much, and yet they're expensive. So the problem is you need a higher utilization rate to make up for the capital cost. One way to do this is to share your battery. So sharing, as in a gig economy, sharing electricity storage. Now, you can't share a fixed battery. If I have a battery installed in my house, one of those nice Tesla Powerwalls, it's difficult to share that with my neighbor. There are issues, there are regulatory issues. The utilities don't like their billing issues. You have a point of common coupling issues. So you can't share your battery over existing distribution infrastructure. A much easier solution is to have mobile storage. So I have an EV, and I'm not using it. I share it with a neighbor. You know, I just drive it over there. So this is part of our broader research on the sharing economy, the gig economy for the grid. The sharing economy works when you have severely underutilized resources. And in the grid, there are lots of underutilized resources. And one of those is electric storage. So I want to tell you a little bit about your electricity bill, maybe not yours, but commercial and industrial enterprises. So of course, these companies, small and medium companies, they pay for their electricity usage. So many dollars per kilowatt hour. It's assessed monthly, and the rate might be, say, 17 cents per kilowatt hour. It might be tiered. It's different in California and in Idaho, but let's say it's that. But there's yet another component of your electricity bill if you're a commercial and industrial entity, and that's called a demand charge. This is assessed monthly. So what you do is you calculate your maximum energy consumption Q assessed over 15-minute intervals over a month. You divide that by 0.25 because there are 4 15-minute intervals in an hour. And so P is your maximum power use in that interval. You multiply that by the demand charge rate, which is around $20, and you pay what's called a demand charge. The demand charge, you're basically paying for peak electricity consumption on a monthly basis. It can amount to as much as 50% of your electricity bill. The reason we have demand charges is so that you are encouraged to flatten your consumption, and so utilities can better plan generation to supply your electricity. So a simple example, this is a particular, I'll tell you about this data later, but you can see in blue Well, before I get there, there's an energy charge, there's a demand charge, and you can see in blue there is a peak. Okay, this is 1 month's data. And if I was to reduce the peak down to the second largest peak, I save around $320, okay? Which is, in this example, around 20% of my electricity bill. So by cutting the monthly peak, a company will save a lot of energy. The utility can better plan for supplying resources to these companies, and so on. So how can we cut electricity peaks? Well, you can have a fixed storage. Oh, that means you're using it very rarely. You can have just an electric vehicle. And so that electric vehicle would serve your company, reduce the monthly peak, go to another company, reduce the monthly peak at the other company, and so on and so forth. So you have high utilization rates when you are sharing an electric vehicle to reduce demand charges across a portfolio of companies. So the strategy might be that I have an electric vehicle, it gets a service request from a company, and that electric vehicle drives to that company location, discharges electricity for 15 minutes, gets a new request, drives to another company, etc. The costs are the battery life cycle, you need a two-way charger, driver wages and benefits, and the business model is viable only if the peaks are temporally dispersed. So if everybody's peak is coincident, then I can't service many companies. Then I would need as many vehicles as I have companies. And of course, you need the costs associated with the charger and wear and tear and driver benefits to be smaller than the benefits. Well, it turns out, surprisingly, that the peaks are indeed temporally distributed. Okay? Now, we have a paper exploring why. You would think it's not intuitive, but certainly the data supports it, and we have some analytical understanding of why. So what I've done here is we have Irish data, we have also San Francisco data, and on the x-axis are metering intervals over a month. And these are, for a lot of companies, 100 companies, and we look at the number of coincident peaks for these 100 companies. There are only 2. This means that I can easily deal with these 100 companies, and I don't need 100 electric vehicles. In this case, I need 2, but if you add drive time, I need maybe 3 or 4 or 5 electric vehicles. So I need a very modest number of electric vehicles to reduce demand charges. You can also look at the data for, this is 17 or 18 months, and there's similar observations from PG&E's San Francisco data set. You need 3 or 5 electric vehicles to service 100 companies, which is very modest. Capital cost, you need a two-way charger. It's sufficient to have a level 2 charger. Capital cost is $3,500, amortized over 15 years, it's $200. And the max discharge rate for one of those chargers is 15 kilowatts. You can have a DC charger, which is substantially more expensive, but you really don't need it. You have to look at the energy costs of discharging the battery, driver side costs. So in our models, we're sort of paying slightly more than Uber. In fact, we can afford to pay significantly more than what Uber pays their drivers, and so on. So I'm going to skip this slide in interest of time and move on. So it turns out that if I have an electric vehicle serving various commercial and industrial enterprises to reduce their demand charges, I'm still not using that electric vehicle sufficiently. So why don't we piggyback on a transportation service? So a joint service provision, electricity and transportation. So when the electric vehicle is not being used to reduce demand charges, well, it can ferry passengers from one place to the other. So when I combine electricity and transportation services, this idea becomes actually lucrative. So there's complementarity. There's temporal complementarity. So we have public domain data in San Francisco on ride sharing. And if you look at demand charge requests, they tend to peak from noon or, say, 11 a.m. to 2, 3 p.m. And there's a lull in transportation requests at that time. You can see it from around 11 a.m. to 4 p.m. And so there is this temporal complementarity. So these electric vehicles that are needed to supply demand charge reduction are now available because they're not being all used to ferry passengers. There's also spatial complementarity. If I look at, say, net drop, this is a map of San Francisco. And if I look at, say, I believe this is 8 a.m., we've done this for all sorts of hours, there's a net imbalance of electric vehicles because everybody is taking rides to the downtown area, so there's a net imbalance. There's a surplus of electric vehicles in the red area and a deficit in the blue areas. But once you optimize transportation and electricity services, you can see there's a significant reduction in accumulation of electric vehicles in the asset fleets of, for example, Uber or Lyft. There's a much better balance of distribution. So what about data? Well, what about optimization? What about learning? So provision of joint services is a very data-intensive problem. So let me give you an idea of what's going on. Firstly, there are many nodes, and you have to conduct optimizations at various nodes. So the platform is, for example, the provider, Uber, and let me move to the next slide. On the supply side, you have many agents. You have drivers of electric vehicles and conventional vehicles. You have, on the demand side, you have also drivers. You have companies that need demand charge reduction on the electricity side. And the platform, that's Uber. The platform sets locational prices, wages for drivers, and fares for transportation services. It's a complicated economic problem, and it's a matching problem across many, many nodes. So it's a very, very difficult problem, and your objective is to maximize profit, do geographic load balancing of electric vehicles, and balance supply and demand requests for both electricity and transportation services. So we are working using the C3.ai platform, terabytes of data. Let's see where we need algorithms. On the electricity side, you need algorithms to forecast in advance with at least a 2-hour latency because the car has to drive to service the demand charge request. You need to forecast when these monthly peaks occur. You need prediction of driver availability. That's on the transportation side. And you need to match vehicles, that's the supply, to demand, both transportation and electricity. You need spatial price optimization. And so it's a complicated, distributed optimization problem. And this is where learning algorithms, the use of data, and the help from C3.ai platform comes in. So what I've presented so far is a commercial proposition. A company like Uber or Lyft would be very interested in it. It's actually more lucrative than transportation services alone because of the complementarity. But what about the value to the grid? Okay, so if one is talking about climate change and so on, one has to take a holistic view of the role of electricity storage, and in particular, mobile electricity storage in dealing with climate change and how it helps. And that's where Utkarsha's project comes in. She's been writing papers on the value of mobile storage in terms of peak shaving, delayed capacity upgrades, improving resiliency, very sort of quantitative paper. And she's got a poster on this, which is somewhere out wherever the posters are. So that is what I wanted to talk to you about. Summary, a viable business opportunity. 15 seconds left, which is remarkable considering I'm on oxycodone and so on. I have extra for those of you who might want some. We're in Miami. It's the oxycodone capital of. So it's a lucrative business proposition. We're talking to Uber, and it's my fault we've been delayed in progressing. I just want to tell you that there's spatial and temporal complementarity. So combining electricity and transportation services is greater than the sum of the parts. That's all I have to say. Shankar.
A wonderful talk. But it seems to me that, it's a dumb pricing scheme in terms of mechanism design about charging 17 cents a kilowatt hour and whatever amount it was for the peak power consumption. So why not revisit why, you talked about the benefit to the grid. What is the benefit to the grid of that particular mechanism design? Why are we taking a line down? That's question A.
Okay.
And then I want question B, you want me to tell you now?
No, let me answer A first because I have limited memory. So why do we take demand charge, the status quo of demand charge pricing? So why is it there in the first place? Okay, because utilities really want to flatten the demand because they can plan for it using a conventional, because even today, a lot of generation is conventional.
But as a tax, it's regressive.
It is, but
so why should we?
So the alternative,
social justice, it's just the wrong thing to buy into.
The optimal thing to do would be to have real-time pricing,
Yeah.
And
now we are talking.
Now consumers are loath to it's something that people want, and a consumer would protest because then they'd have to spend a lot of time planning, and they'd have to. It's just a hard. Okay, as a residential consumer with that kind of price volatility, look what happened in Texas. A few people did sign up for real-time. So what you will need is insurance products. You will need aggregators to absorb the price volatility. You will need things like this. So the answer to your question,
a lousy mechanism.
It is
not an excuse for not having a mechanism.
I agree.
So
but
Texas was a lousy mechanism.
I agree. But this mechanism is there. Utilities are not, how shall I say it gently, are not innovative. They're not risk takers. And it is extremely hard to convince them. The only way you can convince a utility to change is to force it down their throats. Okay? And they are making changes. So for example, time of use pricing is now mandated for all new PV installation, even residential in California. A real-time pricing is not going to happen anytime soon. So if I take Costas's realism, which I alluded to earlier, it is nice to say, well, why don't utilities do this? They don't. They're not going to unless they're forced to. So in the interim, we have to find value to the grid. We have to decarbonize. One can come up with solutions to climate change. Do we have the political will? No. We'll have to do what we can. That's my answer to your question.
Okay, I'd love to debate it because I don't agree. But having said that, let me ask a technical question. You talked about matching problems. Something I've also worked on. It's hard enough to do matching problems for small numbers. So you're going to do this over, you think at the scale to tens of thousands of, or what makes you think that those matching problems will scale to large numbers of agents? This is a more technical question.
Okay. So first, we don't have to do matching problems in the tens of thousands because these are geographically localized problems. A vehicle in San Jose is not servicing demand charge reductions in Oakland because the drive times are prohibitive, okay? So we're talking about local optimization problems where sort of we're talking about a couple of hundred maximum electric vehicles, and with penetrations of electric vehicles being what they are, we're talking about, of these assets, maybe 20, 30, 40 electric vehicles. So it's not an intractable problem. And in some papers we've written, we've sort of convexified, we've done convex relaxations of these matching problems, and it is within reach. And the level of suboptimality can be bounded. It's all, I deliberately didn't put any mathematics in here. But it's not, the short answer to your question is we're talking about geographically localized matching problems. And our consultant to this is Alvin Roth. So, but I'd love to debate A because I think, I appreciate and respect your optimism, but I think.
I don't see how the solution actually addresses what it does for the grid. Because you're taking the main lever that you have. And by the way, utilities don't operate. We have public utility commissions in every single jurisdiction that is able to influence their pricing policy. So we, the people, actually are able to influence.
Okay. We the people, where shall I start? We the people in the current political reality it's not a democracy. Okay, so we the people, okay, that's one. Two, there are public utility commissions. They're elected officials. As with all elected officials, their primary concern is to be re-elected, okay? And, they're not, this is a problem that I am not able to, I don't pretend that, we can solve. I think I just want to solve what is put in front of me, and I don't think, look how long it took for time of use pricing to appear in California. It's, and let alone, Texas or the rest of the grid. Real-time pricing is, it is there, but it is done through risk aggregators, through insurance products. So it's just, utilities are not agents of change. They're agents that resist change. I'm sorry if there are people here from PG&E or Florida Power and Light, but I just think one can plan, one can work on problems 40 years out, 5 years out, somewhere in the middle. But I think we have to work on all these problems. I'm not suggesting that one only take a myopic perspective, but I think we work on all timescales. That's my rejoinder.
Well, thank you so much. Let's thank the speaker one more time.